Welcome to another video in my series, Force Method versus Method of Stroops. In this video, we analyze this truss using the method of Stroops. This problem is taken from the video Essay 26 Force Method Truss Analysis from about 3 minutes into the video. I think this video is by Dr. Structure, and it's a very good video. The link is in the description. You don't have to stop viewing this video and go to that one first. Just continue with the current video, and later you can go to Dr. Structure's video, where he does it using the force method. In this video, of course, we use the method of Stroops. Now, the thing to observe in this structure is that it is externally statically indeterminate. Internally it is determinate, but because you have a hinge joint here and two rollers, then it is externally statically indeterminate. Dr. Structure's video explains the idea of external static indeterminacy. Now, this kind of stroop, I have not done examples of external static indeterminacy using the method of Stroops before, and I have not analyzed anything of this stroop similar to this in any previous video. So this is the first challenge that I have met using the method of Stroops. I was not sure if my method of Stroops could handle this type of structure, externally statically indeterminate, and not a typical type of stroop. So I thought I may have had to make another video entitled The Force Method Strikes Back and admit that my method of Stroops was inadequate. But I do not have to do that. You will see in this video that the method of Stroops can handle this quite easily, and in fact it has many advantages over the force method. So let's start with the method of Stroops. We will proceed to analyze the structure using the method of Stroops, which I developed in my video Trusses, Electrical Circuits, and Kirchhoff's Laws. And I've used this method in other videos. So after this video, you can also view this video on Trusses, Electrical Circuits, and Kirchhoff's Laws. The first step in the method of Stroops is the transfer of forces to the supports. That is the transfer of the externally applied forces to the supports. The only external force applied is the 10 kilonewtons at C. And you can do the transfer to the supports in different ways, but in this case I'm just going to assume this 10 kilonewtons is equally balanced by these two forces in BC and DC. So I'll have zero force along this diagonal, and this is split equally in these two directions. And from the slope of this line, you get the compressive force in this member to be minus 5 root 29 over 2, and the same compressive force in BC. Now here, because it's on rollers, to have equilibrium vertically, you need a compressive force -5 in AB. That will balance the vertical component from the force in BC. And to balance the horizontal components, you need a horizontal force of 25/2 horizontally from the support at B. That's to balance this. So this will give you equilibrium at B. For equilibrium at D, since it's on rollers, the vertical component from DC must be balanced by the vertical component from AD. So you need -5/5 in compression in the member AD. And to balance these forces horizontally, you need an external force from the support of 45/2 in this direction at D. Of course, we can easily calculate the horizontal and vertical components at A. I'm not doing that in this diagram, but it's easy to see that this 10 kilonewtons here must be balanced by an upward 10 kilonewtons at A. And to balance horizontally, you can work out the difference of these two and get the horizontal reaction at A. But this will give me a balanced set of forces, so this transfers the external forces to the supports. So we will use this in the analysis. Just remember, what I'm doing here is basically the method of joints, which you will see in other videos. And this is nothing different to what you would do in the force method. So up to here, we are doing basically the same thing as we do in the force method, except for the fact that we don't specify a determinate substructure or primary structure or anything like that. In fact, this structure is more or less internally it's determinate, but we because of the reactions here, it's externally indeterminate, and we can choose arbitrarily to let the force in this member be 0, and that will give us an easy way to get the remaining forces. Once again, this is not a typical type of Stroop. It's not the rectangular or parallelogram type of Stroop that we've seen before. And of course, the internal members do not form a Stroop because it's internally statically determinate. So what we do is we apply what I call external Stroop forces here. This is 5/2 F at B, and opposite to that you have 5/2 F at D, both horizontally. And it's the same idea as having a member from B to D. If you had a member from B to D, it would form a Stroop. You would have 6 members, which would form an indeterminate structure, which would be a Stroop. And for that reason, we will use these external Stroop forces, and from those we calculate the forces in the members of the structure. Okay, so I've used 5/2 here just so that I can get a force of F in AB, and using equilibrium you can get these other Stroop forces at, on the other members, okay, simply by applying equilibrium at the joints. So these are our Stroop forces. Notice here, although it's not indeterminate internally and there's no internal Stroop, by these equal and opposite external forces, which are equivalent to having a member at B, we can create these Stroop forces in the members. So we will use these Stroop forces in our analysis. In this diagram, I have superposed the previous two diagrams, the transfer to the supports and the Stroop forces. So you can see the sum of the forces on the side of each member. These are the sums of forces. Okay, now in red here, I have the external reactions. Okay, so it's 25 over 2 plus 5 over 2f, and here it's 45 over 2 plus 5 over 2f. So that's the total of the superposed and the total superposed force at B and D. At 10, the reactions would be, at A, the reactions would be 10 horizontal and 10 vertical, which I did not show on the previous slides, but can be calculated quite easily. Okay, of course at C you have a 10 vertically downwards. And these are our superposed forces. So we go to the next step in the method of Stroops. Now, once we have the superposed forces, we need to form the compatibility equation. And this diagram gives us the coefficients for the compatibility equation. Now, as I said, we do not have a typical type of Stroop here. It's something that I had not seen previous to this example. So I had to work these coefficients out from first principles. Later on, I will give more details on how I obtain these coefficients, but these are the coefficients I got for deriving our compatibility equation. We are working under the assumption, as we said at the beginning, that all cross-sectional areas are equal. Okay, of course, the compatibility equation will have to take into account the cross-sectional areas of the members. So once that is taken into account, these would be the coefficients. These are the diagrams from the previous two slides that I've copied and pasted here. Coefficients are on this diagram and the superposed forces are on this diagram. The compatibility equation is obtained by multiplying the coefficients times the superposed forces for each member. So each member will multiply the coefficient with the corresponding superposed force, and we add these terms first around the perimeter. You have four terms here on the perimeter, and then equate that to the product on the diagonal. So if you look at this term, for example, 9 by 29 by this thing, that's for the member BC, and then 5 by 29 by this force, that's for the member CD, and then 250, that's this number times 5 root 5 into this, that's for this member, and then the 90 times the minus 5 minus f for the member AB. So these are the products along the perimeter summed on the left hand side. On the right hand side you have the product here, 4 by 74 times this Stroop force times this superposed force. So this is our compatibility equation. I've done it in an algebraic way here. So it's a matter of solving this equation. There's just one unknown here, and we will proceed algebraically to solve this. So here is the compatibility equation, just copied and pasted from the previous slide. There's just one unknown here, which is f, so I put the terms in f on the left hand side, so it's f into this bracket equals, carry the terms without f on the right hand side, and these are the terms without f. And when you simplify this, when you calculate these values, you get f equal to minus this number divided by this number, which works out to be minus 4.6186. Now once we have f, we can substitute this value of f into the diagram with the superposed forces, and that will give us the solution for the forces in the members. So let's look at that in the next slide. So here is the solution. I've replaced the f by the value minus 4.6 from the previous slide, and I've obtained the forces in each of the members. Okay, notice I've obtained the reactions here also, because the reactions at B and D depended on F. So I was able to obtain these reactions at the roller supports, as well as the forces in each of the members. The reactions at A are fixed, minus 10 horizontally and also vertically. And this is exactly the same solution as obtained using the force method. In the video by Dr. Structure, these were the exact numbers obtained using the force method. So all of this shows that the method of Stroops is correct. It gives the correct results. It gives the same results as the force method, and in my opinion it involves less work, and it is also more intuitive and understandable from a structural analysis point of view. So I'm not a great fan of the force method or virtual work methods. I think the method of Stroops is a better method, both in terms of the concept behind it and also I think in terms of computation. In another video I will say more on the computational aspects. I will use the spreadsheets to actually do all of the computations. Instead of all the algebra that we've been doing, I will do all of those calculations on a spreadsheet. Thank you again for viewing my video presentation here, and as I've said before, this should be very helpful to students doing engineering or applied mathematics or structural analysis. My name is Charles DeMatteis. I'm a retired lecturer from the University of the West Indies. St. Augustine campus located in Trinidad. And it's thanks to the generous support and patience of the university that I'm able to make these videos and post them. I'm looking for other sources of sponsorship, but right now the university is helping me very considerably in making these videos. I don't know how long I will continue getting support from the university, but I just want to put out my ideas while I can on the method of Stroops, which I think is a step forward in structural analysis. I know everything now is focused on computer software and things like that, but I think there is some kind of benefit in doing these things algebraically also. It gives you an understanding, a feel for what is happening. So once again, thanks for your attention, and I hope you will view more of my videos and possibly like and subscribe to my videos. Thanks again.